want to welcome you to another week. Of course, I said the other time, statistics is like a story, and a story that goes on and on and on. Before I start today's lecture, I realized that the recording for the other time was has a very good quality, and I've already published that on the YouTube in case you want to watch that. Of course, you put my name on the YouTube, you're going to have access to that. I'm also recording this. So the moment this come out good, I'm also going to publish that. So I want to welcome you to another interesting statistical topic that we'll call central limit theorem. And of course, this is going to be from another chapter from the recommended textbook. I've uploaded this updated material. You can check this on YouTube. Okay, so in the outline today, I'm going to revisit the law of large numbers because I need to be able to, to explain relationship, if any, between the law of large number and the central limit theorem. And I also quickly want to mention, as far as law of large number is concerned, we got two types of law of large number. So today I'm going to tell you, walk you through what is different between the weak law of large number, the one that we abbreviate as WLLN, and the strong law of large number. Then finally, I'm going to go into today's topic, which is the central limit theorem. I needed to sit back and, ask questions where necessary. There's a kind of connection between the law of large number and the central limit theorem. But you know what? I'll first go, I'm going to have a recap on the law of large number. Of course, in the law of large number, what we're trying, we believe that if I have a random variable y, like y1 up to yn, okay, that has mu and, finite variance or standard deviation, okay, we believe that when sample size become large, when sample size tend to infinity, we actually expect the sample mean to converge to population mean, okay, within a certain, distance, k standard deviation from the mean. Now, what I'm trying to showcase right now, okay, this is actually the one we did before. The law of large number we did before is actually called the weak law of large number. Why is it called weak law? It is called weak law because the sample mean does not converge to population mean absolutely, but we actually, the convergence is actually within a margin. You can see epsilon, right? You see epsilon, right? So we're trying to go ahead. Yeah, weak law of large number. Exactly. So which means the one we did before, the law of large number we did before, we only focus on the weak law. And what makes it a weak law is, if you take a look at this mathematical expression, give me 1 second. If you take a look at this guy here, okay, if you take a look at that guy, we're looking at the probability of the absolute difference between the mean and the population mean within a certain margin of error, like the epsilon. Yes or no? So that probability that the distance between the sample mean and the population mean would be within a particular margin is what we believe is going to be 1 if n tends to infinity. Okay, so this is called the weak law of large number. It is a weak law because the convergence here is not absolute. We are actually seeking the convergence within certain margin. Okay, but I'm going to show you, before I go into this, I'm going to show you this. I define it here again. The whole thing actually starts from a random variable y1, y2 up to yn that are high ID. Of course, you know, they actually come from a normal, a particular distribution. Okay, and they are independent. And we know the mean, the expected value of yi is equal to mu, and of course, the standard deviation is this. Now, if we're seeking for this guy, if you take a look at that guy, that's a sample mean, right? Which is the addition of that. So what are we trying to do? Because I told you the other time, we're going to have more than one sample mean. If 1,000 investigator is to go into a particular population of interest and we take a sample, okay, the same sample on the same study, we're actually going to have different means, sample means. Okay, now if you take a look at the next one here, if you take a look at that guy, okay, we're focusing on probability of convergence. As n tends to infinity, as the sample size becomes infinitely large, okay, now when you take a look at this, I want you to pay attention to something. When I put greater or equal to SN, the probability will be 0. Okay, now greater or equal to SN, you're trying to say when sample size is large, the probability that the absolute value difference between the sample mean and that will be greater than. We don't want it to be greater than, we want it to be less than. Okay, so what we're trying to say is that it's not possible, like it's going to be 0. And if it is less than, I'm going to put 1. Does that make sense? This is still weak law of large number. And if I want to write that in short form, what am I saying? That's a convergence in probability. Can you see P, right? It means the sample mean converges to population mean in probability. Convergence in probability actually means the weak law of large number. Does that make sense? That's convergence in probability. Now, I want to walk you through strong law of convergence now, the one that we haven't done. Okay, now the one we haven't done, give me 1 second. I'm going to clear this right now. Now, I need to take a look at strong law of large numbers, strong law. Okay, in terms of statistical architecture, what is the difference between the strong law and the large and the weak law of large number? Okay, I told you the weak law of large number actually under the convergence in probability, but it's not absolute. Okay, we actually considering the convergence of sample mean to population mean, okay, within a certain distance. You understand what I mean? That's why we have SNM. But take a look at this. Don't forget, we're still focusing on the sample mean, right? Which is that guy. The xn is a sum of the observation. There's no way I'm going to pass through. There's no way I'm going to pass through the sum of observation. If I want to figure out the sample mean, I'll need to for sum, right? Then I get the sample mean. Now I needed to pay attention now to this guy. Do you see any epsilon? There's no epsilon. Here we're looking at absolute convergence, not within any distance. The other time was the probability of the absolute value difference between the sample mean and the population mean less or equal to epsilon. That means we're looking at that within the distance, certain distance. The epsilon, don't forget, is the K standard deviation. You know that? K multiplied by the standard deviation. That's a distance. You're trying to say there is a K standard deviation, sample mean converges to population mean within the K standard deviation of the population mean. That was the weak law of large number. But right now, you're trying to say when the sample size increases, okay, the xn, which is sample mean, will automatically converges to population mean, and that probability is going to be 1. And I needed to take a look at this. What is the meaning of that AS? That is almost surely. Okay, that's an absolute convergence. So this is the strong law of large number. The strong law of large number is different from the weak law. Any question on this? On the difference between the two? Any question? Go ahead. Like the omega. Oh, okay, give me 1 second. I'm gonna are you talking about this one? Okay. The other omega is the sample space, like collection, the omega has a lot, when you are dealing with probability, we need to have a space for possible outcome. So we're trying to say for every outcome W in the sample space. Does that make sense? That now depends on what you are looking for. Okay. For every, that means the other E means lies. So the probability when W lies in the omega is like sample space of possibility. Okay. We expect that the Xn, okay, which is a function of that W. Where's the W coming from? The W is coming from the sample space. Okay. So that is going to be equal to mu. Okay, with probability 1. I don't know. Did you get it? Exactly. No matter which sample you take, because your sample has to be large. Do you see when we talk about sample? What talk about sample is this guy? The n tends to infinity. Okay, it's what talk about sample. Because if you say no matter sample you take, it's not going to work for small sample. Exactly. No matter which individual you choose, because individuals are independent. That's a good question. That's an assumption. The people you are choosing from the population, no matter, because you are assuming that they are independent. That's a good question. Okay, now I think I've differentiated between the weak law and the strong law of large number. Now I want to revisit the law, that again. Now take a look at this. This is going to take us to central limit theorem now. Suppose y1 up to yn iid, okay, come from this guy. Okay, come from this guy. If y1 up to yn is a continuous random variable, that guy is going to be a PDF, right? Every random variable has probability distribution, whether discrete or continuous. Does that make sense? Okay, now that PDF has a mean and standard deviation, and we can calculate mean. Okay, now do you know that if we know the distribution of y1 up to yn, we can make a conclusion about the sample mean. Of course, we all know the random variable y follow normal with the mean. What is the expected value of y? Mu. What is standard deviation of y? Any y, whether y1 or y2 or y whatever, is going to be sigma, the standard deviation. Now, if I now want to figure out what is the expected value of sample mean, of course, I've demonstrated that, right? Expected value of y bar is going to be mu, and the variance of y bar is going to be sigma square over n, because we've used the law the other time, linearity of expectation and the linearity of the sum of the variance. So this actually coming from where you already know the distribution to be normal. Okay, when you know the distribution of a random variable y, you can actually generalize that on the distribution of the random variable y bar. Okay, so the variance of y is sigma square, but the variance of y bar would be sigma square over n. And of course, the standard deviation of y bar would be the square root of that. Okay, now this is a situation where you know the underlying distribution of the random variable. Okay, and by the law of large number, of course, when I say the law of large number, and you see me writing this guy, of course, as you know, I mean the weak law. Does that make sense? That's a weak law of large number. Of course, we showed that the other before, right? Let me tell you this. When a random variable follow normal distribution, it is not automatic that the sample mean will follow normal distribution. Okay. Now, what I'm trying to say in essence here is that is going to happen when the sample is sufficiently large. Now, by way of law of large number, particularly I'm talking about the weak law, for epsilon greater than 0, I showed you last week how the probability of convergence, okay, convergence between the sample mean to population mean within epsilon is going to be 1. I remember when I was varying the sample size, you saw that probability of convergence was actually increasing to 1. Yeah, go ahead. You don't understand what? Oh, that's a very good question. When you have a less than inequality sign, then it's going to be equal to 1. When you have a greater or equal to equality sign, it's going to be equal to 0, which means this is a complement of the other one. Does that make sense? That's a very good question. Do you know the question she asks now confused me when I was in college? At times I see greater or equal to, at times I see less than. What is the meaning here? Oh, complement. That's what it means. Okay, which means for less than epsilon, the probability of convergence is going to be 1. But for greater, which is the opposite of that, the probability of convergence will be 0. That's what it means. Now, and I just said right now, if we know the PDF of the underlying distribution, we can actually conclude on the probability density function of the sample mean. But do you know what we want to do today? What of in a situation where we don't know the distribution? Okay, when we know the distribution, inference will be very easy to do, right? When I know the distribution of random variable y, I can actually talk about the distribution of the y bar. That is, if I know the underlying distribution, when I say I mean probability distribution, and that was why if you take a look at the question, okay, what of in a situation, can we say more about the distribution of that in the absence of normality? What of in a situation where it is not normal, where the distribution is not normal? Maybe I know the distribution, but it is not normal. Because in statistics, we got different types of probability distribution. Okay, so, we have, they can be generalized, they can be divided into 2. We have a symmetric one and the asymmetric one. The symmetric one is a normal. The asymmetric one, there are so many of them. Exponential, Poisson distribution, Weibull distribution, chi-squared, beta, gamma. There's a lot of them that are not symmetric in nature. Okay, now let's say the distribution is not normal. Okay, what can we say about the distribution of y bar? Is the distribution of y bar still going to be normal, even though the underlying distribution of the random variable is not normal? Is there something we can do to make it normal? Oh my God, that is why we need a central limit theorem. You can see statistics like a story, right? It's like a story. Like if I want to listen to any lecture, I think I need to know what is behind the scene. Why am I doing what I'm doing? Now you know why we're doing central limit theorem. We want to go into central limit theorem now, because what if the underlying distribution of the random variable is not normal? What can I say about the distribution of the sample mean? You know what we're going to do? That is going to take us to simulation. I'm going to attach a material today. For those of you who use R software, how you can do simulation in R. And I'm going to walk you through this right now. And I need you to pay attention right now. Okay, now let me just tell you, before going into this simulation process, the central limit theorem actually provides us an opportunity. Okay, with if what we need to do, if the underlying distribution is not normal, something that can be done to make it normal. For instance, the distribution of y is not normal, and I compute the sample mean. Okay, what am I going to do to make sure the distribution of the sample mean is going to follow normal? Why am I interested in following normal? Because with the normal, I know the expected value of y bar is going to mu. I know the variance of y bar is sigma square over n. I know the standard deviation of y bar is sigma over square root of n. Okay, if we can do something to make it normal, okay, we got easy formula to use. Okay, so the law of large number actually tell us sample mean converges to population mean when sample size is large. That is the law of large number. But the central limit theorem actually talk about how you can attain normality even though the underlying distribution is not normal. The two are not the same. Okay, let's go into simulation process now. Take a look at this. Let's say the underlying distribution of the random variable is exponential. Has anybody seen exponential? Have anybody seen this probability density function before? Okay. You know, we got a way in statistics to investigate the distribution of data. When you are working with data set, a statistician, you need to first investigate the distribution of the random variable. Okay, so we have so many. You can look at the histogram. You can go, there's a test in R called Shapiro Wiki test of normality. We have a Kolmogorov or Simonov test, a Dacidali test. We got so many tests. You know, if I really want to figure out what is the distribution of my random variable now, right now, maybe I've already investigated that, and I realize the distribution is exponential. Okay, exponential distribution is statistics is used to model waiting time before the occurrence of an event. How long am I going to wait until this guy is no longer going to work? It's not going to work forever. Efficiency of any equipment is not 100%. So how long am I going to wait? We use exponential distribution for that. Now, if I actually use compute the mean from data set that follow exponential distribution, how can I attain normality? That is the essence of this simulation process. Okay, now the experiment is going to start. We're going to draw a sample, y1, y2 from the exponential distribution. Okay, parameter beta. Okay, now, you know, if we want to start, okay, we can let the beta to be something like if beta equal to 1. You know, if beta equal to 1, I'm actually going to have f of y equal exponential is power minus y, right? When you plug in 1, okay, the rate parameter, that is actually, you know, we set that to 1. So in a simulation process, you can set it to a number. Does that make sense? We set it to 1. Okay, now when we set it to 1, okay, but let me tell you this. You need to first understand, you know, theoretical, you know, properties of the underlying distribution. I know when I have f of y equal to that, expected value of y is going to be beta. You know that? Like if you remember what you've done in a lower course where you know, You see that? So you have to know that. That is expected value of y is beta. The variance is beta squared. The standard deviation of y is beta. You have to know that, okay? The underlying distribution. Now, we're actually going to choose a random sample from there. Now, take a look at this. When you choose a random sample from the distribution, we advise that you vary your sample size. Vary your sample size. Go from small sample to moderate to large. Okay? Now, because we want to test the sampling properly, now I needed to take a look at this. I said, we actually want to find the mean, sample mean. And of course, sample mean is just going to be a single realization of that. Okay. Now, to find the distribution, we need a distribution of y bar. If I want to get a distribution of y bar, then I need to do, I actually need to take, like, for instance, take a sample. Okay. And that sample will be repeated. And that was why I said, repeat above step m times, where m tends to infinity each time. M tends to infinity each time. Now, I needed to take a look at the data now. In simulation study, we do replication. Okay. Now, take a look at that. If you take a look at the first set from y1 to yn, this is like the first set of when, the first replication, you find the mean of that. The second replication, find the mean of that. Okay. At time we could do 1,000 replication. Do you know I can take a sample size of 20 in 1,000 ways? How many, and in each repetition, I compute the mean. How many means am I going to get? That's 1,000 mean. If I go in 1,000 ways. Does that make sense? Okay. Now, if you want to do this, we do this for small sample, for moderate sample, and for the large sample. Now, we can now plot the histogram. I told you the other time, if I want to know the distribution, of course, I can figure out the distribution for the histogram. Okay, of that. And histogram will give us the approximately the PDF of y bar. Don't forget, what we're seeking is a PDF of y bar. Now, you know what happened? When you choose a sample size of 2, it's not going to be normal. I told you, vary your sample size. That will give you opportunity to see, the way it is distributed for small sample size, for moderate, and for large. Okay. Now, take a look at the first one here. Give me 1 second. When you take a look at this guy, that is not normal, right? Based on sample size 2. We increase that to sample size 10. It's still skewed, right? We now move to sample size 50. From sample size 50, we move to sample size 200. But there's something I really want you to see. What is the takeaway here? When I increase my sample size, then the shape of the sample mean will converge to the shape of a normal distribution. Take a look at that. That is what central limit theorem is telling us. Whereas sample size increases, okay? When sample size is increasing, we expect the distribution of the sample mean to converge to normal. Does that make sense? Okay, that is what we have, that's what we have here. And if you take a look at for sample size of 50 and the sample size of 200, I may decide not to go to sample size of 200. But let me just tell you this. If we want to use the rule of thumb, okay, how large is the large? Do you know we can achieve normality with sample size of 30? When your sample size is 30, we can achieve normality, because from 30, you're actually going to see the center. The center is going to be 1. Can't you see? The center is basically going to be 1. Basically going to be 1. Now, take a look at this. I said, find this. When sample size n is large, the histogram of y bar is concentrated around what is the true value of the mean. the true values of the mean is what you got from the distribution. I told you the other time, what you see here, give me 1 second. Do you see, I'm going to clean this now. Those are the true values. The true values of the mean and the true values of the variance and the standard deviation. Don't forget, you set that to 1. In a simulation process, we're actually going to pretend we know the truth already, right? I know what I ate yesterday. Okay, maybe yesterday I ate an African food and I say, okay, this guy presents himself to me as a statistician. Before I'm going to tell this guy to tell me what I'm going to eat tomorrow, I'll first say, sorry, can you tell me what I ate yesterday? I know what I ate yesterday. I asked that question for me to be able to have some, maybe how I can trust him. So here in simulation study, we know the truth, but we want to figure out what are we going to do, what sample size are we going to have before we can actually have the truth. The mean is 1. Okay, when you see the expected value of y equal to beta, we set beta to 1, but in the end, you can see here that actually converges to 1, to the true parameter we set at the beginning. Look at that. It doesn't matter what you set. Even if you set 2, here we set 1, right? You can set 1.5, you can set whatever. When the sample size is large, it's going to converge. The sample mean is going to converge, even though if the underlying distribution is not normal. Now, because of that, see number 1, it's going to be concentrated around that. Concentrating around that, you're borrowing idea from the law of large number, which means the sample mean converges to population mean. The population mean here was 1, right? Beta equal to 1. And what happened? On the long run, the sample mean converges to population mean 1. Now, number 2, not only that, the shape of the distribution. Initially, it was an exponential distribution, but right now, the distribution of the y bar approximately follow normal distribution, as you can see, as it's demonstrated in the histogram. Take a look at that. Can't you see statistics is beautiful, right? Statistics is beautiful. Okay, now I have a question here. Okay, question, normal with what mean and variance. The moment we're able to establish the fact that the sample mean is approximately normal, then we can actually use, we can figure how, what the mean and the variance is actually going to be. We're going to say, okay, the y bar now follow normal distribution with the mean beta is 1, with the variance sigma squared over n. What is sigma squared for the distribution? What is sigma squared? The sigma square is beta square. You know that? That was why you see beta square over n. Any question? Any question? Okay. Now, there's something we can do again to verify. Okay. We can verify again. See, to verify our finding here, we can use simulation to find the distribution of this guy. You all know standard normal distribution, right? The standard normal distribution is, the mean, the expected value of a z is 0, right? The variance is 1, right? And I told you why we use standard normal distribution. Okay, we want to restrict the values of mean and variance, to a particular value, so that we don't have an infinite numbers of pages for statistical table for z. Now, we take a look at this guy now. Okay, if y bar is approximately normal, Okay, we expect the Z to also approximately, normally distributed with the mean 0 and variance 1. We can demonstrate that. This is what we're going to do. Take a look at the simulation again. We're going to go into simulation again. Okay, we're going to have M repetition. Now, if you take a look at this guy, that is the mean that we got from repetition number 1, right? Now, from that mean, you know what we're going to do? We can compute the Z, right? We can compute this guy. What am I using? The sample mean minus the population mean. What is the population mean? Beta divided by the standard deviation of y bar. Don't forget, standard deviation of y bar, sigma over root n, but the sigma for the exponential is beta. Any question? Now we're going to do that across. We're going to have Z1, Z, like up to that, and in the end, we can plot that. When we plot that, let's take a look. Oh my God. Take a look at that. Take a look at what we have. You do the same for where sample size increases. In the end, if you take a look at sample size 50, what can you talk about? Look at the middle, look at the center. 0, right? The mean is 0. Okay. And when you take a look at the standard deviation here is 1. And therefore we can say the Zn approximate, normally, follow a standard normal distribution only when n is large. Because when n is not large, there's no way it's going to converge to that. Now, I want to go a little bit theoretical now. Let's look at the theorem from the textbook. We're talking about central limit theorem now. Okay, if we have y1 up to yn, they are independent, identically distributed random variable. Okay, they they don't necessarily follow normal. They could follow a different distribution, but whether they follow different distribution or not, you know the mean and the variance of the distribution. Just like for the exponential, I told you in the exam, I'm going to allow you to call me with a tape, list of, there's going to be something that contains a list of distributions with the mean and the standard deviation. You need them. Okay, now if you take a look at this, define this. What are we defining here? That's a standard normal distribution, right? The standard normal variable from where? That is actually going to come from the sample mean. And we believe that the distribution of UN, which is our Z now, converges to standard normal distribution as n tends to infinity. The central limit theorem focus on that convergence from a distribution to normal when the sample size is large. And the way we can look at it is we can look at the convergence to standard normal distribution. Okay, so take a look at that. And that was why I say UN. Take a look at this. If I want to find the probability of UN less or equal to U, like a CDF, CDF, right? Where n tends to infinity. Okay, if I start from a normal distribution, okay, at the end of the day, I'm actually going to find myself, look at that, what density function is that? That is standard normal distribution. When you have 1 over square root, initially this is what you have. Initially, that's what you have. That's a normal distribution. Okay. Now, with that is going to converge. So I'm just trying to tell you this is a normal distribution. That's a standard normal distribution. Let me tell you this. We can use central limit theorem on a normal distribution. We can also use central limit theorem on a distribution that is not normal. It doesn't matter. Okay, so take a look at that. And here, you know what that means? Oh, give me one. Let me clean this so that you actually gonna. Okay, so take a look at this guy. What that guy is telling me, the UN converges in distribution. You see D, right? Converges in distribution to that as sample size become large. Okay, now the remark is now going to be, I may decide, I may want to find what is the probability of a Z lying between A and B. Of course, it is the same thing as that. It means I want to find the integral of that from A to B. That's exactly what I want to find. But how large is sufficiently large? Then it has to be at the rule of terms say it has to be at least 30. Does that make sense? That is and that is the reason why in statistics, you know, we require that the sample size should be at least 30 before the sampling distribution of the sample mean we actually converges to normal, even though the underlying distribution of the population is not normal. But let me tell you this. If the distribution is normal, I'm going to say this again. If the underlying distribution is normal, irrespective of the sample size, the sample mean will be normal. I'm going to say that again. If the distribution, if the underlying distribution of random variable is normal, okay, irrespective of the sample size you choose, whether small or moderate or large, the distribution of the sample mean will be normal. But if the underlying distribution is not normal, then you need a sufficiently large sample for the sample mean to be normal. And how large is a large? It has to be at least 30. Does that make sense? Okay, before I go, there is one particular in the new assignment I gave. I think I put an exercise here. You know, I really want to explain that so that you'll be okay. Take a look at this. I gave something that looked like this in the new assignment too. Now take a look at this. You know, let f of s be equal to 5 over s squared. Is that s squared or s6? Sorry, x6. For s greater or equal to 1 and 0 otherwise, you have a probability distribution. You have the state space, right? 1 to infinity. What bound does Chebyshev inequality give for the probability? I want you to figure out what is the probability of s greater or equal to 2.5. Let me tell you. If you want to calculate that, if you want to use the for actual value, okay, if you make use of the distribution directly. For instance, if you take a look at that, if I want to find what is the probability of s greater or equal to 2.5, that would be integral 5 divided by s raised to the power 6, the s, what is going to be the state space from 2.5 to infinity. Does that make sense? With that will give you the actual probability. But what if I ask you to use Chebyshev? This is a way. If I wanted to use Chebyshev, okay, the result that we go to, if you want to use Chebyshev, you need to 4 start. Don't forget in the Chebyshev, the probability, you remember the probability in the Chebyshev, you need to figure out what your K is, right? When you have an epsilon, you need to figure out the epsilon is going to be K standard deviation, right? K standard deviation. Therefore, you need, what does it mean here? What is the standard deviation? What is the variance? You know, you got the mean and the variance of the distribution. Now, you want to find the probability of s greater or equal to 2.5. You can rewrite that as this. You see that? Why am I using greater? Because in the question, do you see the question? The question is the greater, right? Now, if I want to rewrite s greater than 25, I mean 2.5, okay, now that is going to be equal to s greater or equal to 5 over 4 plus 5 over 4. How do I get 5 over 4? Because we're talking about x minus mu, absolute value, and the mu. What is your mu? You see 5 over 4 that you've computed. So if you want to rewrite that, okay, that is actually telling you, okay, that you actually want to find the probability of this greater or equal to that. So which is going to be s greater than or equal to 2.5 or s less or equal to 0, and all what you just need to find what is the k. If you have your k, don't forget, when you have a greater than here, it's going to be you remember 1 over k squared. If it is less than, that will be greater or equal to 1 minus 1 over k squared. Because right here, they're talking about greater than, right? And that is the reason. So you can see, now I got sigma squared divided by that, k squared. Take a look at that. And the result is 1 over 15. 1 over 15 for the chef. If I ask you to find the actual value, then you're just going to integrate 5 divided by x over 16, then the state space is going to go from 2.5 to infinity. That would be the actual probability. I told you the other time, chef probability is not the actual one. It's just the minimum, okay, that you can get. Any question? In case you need a clue on that. I think the other is where I'm actually going to stop today, and what we're going to do next is going to be the application of central limit theorem. Any question? Okay, my office hour every Tuesday, 10 to 12. In case you need clarification, make sure you meet with me during my office hour. In the absence of question, make sure you all stay safe and have a lovely day. Bye for now, everyone.